MASW stands for Multi-Channel Analysis of Surface Waves. It is a geophysical technique, and its original technical contents were published in Journal Geophysics in 1999. It is a seismic surface wave technique to generate shear wave velocities of near-surface ground materials, usually shallower than 30 meters. It has applications mainly in geotechnical engineering, such as a seismic site characterization, also known as a VS30 measurement, and bedrock mapping, soil bedrock characterization, and anomaly detection. This shows an overall procedure of MASW survey, which consists of 3 simple steps. First, you go out in the field and collect so-called multi-channel seismic data by using multi-channel data acquisition technique, which uses this kind of multiple number of receivers, which is called receiver array. And then the collected multi-channel data will go through 2 steps of data analysis. First one is called the dispersion analysis, and second step is called the inversion analysis to finally generate this kind of shear wave velocity profile, which shows shear wave velocity variation with depths at the center of this receiver array. And this kind of profile is often called 1D profile because it shows velocity variation along only one direction, which is depth in this case. So generation of this kind of 1D shear wave velocity profile is the ultimate product from MASW survey at one location. And this one shows a schematic of typical MASW field survey. In this case, it is a 24-channel data acquisition, and there are 24 geophones planted along this linear trajectory. And there is also a seismic cable laid down, which has 24 takeouts, evenly spaced, like 1 meter, and each geophone is connected to each takeout. And then each geophone, which has a plus and minus polarities. And therefore, there are 2 wires from each geophone are connected into each takeout. So a total of 48 wires are cased within one common seismic cable. And all of them are connected into this device called multi-channel seismograph. So this is a 24-channel seismograph. And then when you make an impact by using a typical seismic source like a sledgehammer, which has this kind of hammer switch attached on the handle, then the hammer switch detects the impact and sends a signal into this seismograph to start recording. So as the generated seismic waves, which are propagating into all directions, are passing through this geophone array, their vibrations are picked up by each geophone. So each geophone's vibration history will be transmitted as an analog signal into this seismograph, and then converted into digital data and transmitted into this field laptop computer, where all those 24 sets of digital data will be saved as one file, which is commonly called one MASW file or one MASW field record. And then the collected field record will go through dispersion analysis first, in which a field record will be transformed and generate one dispersion curve. So this is one measured dispersion curve, and the specific shape of a dispersion curve is determined mainly by the subsurface shear wave velocity structure. Therefore, it is very, very critical to come up with as much accurate dispersion curve as possible. And then the measured dispersion curve will be passed into next inversion analysis step. At the beginning of this step, the program will generate an initial velocity model, which is a kind of approximation model, regarded as something like only 50% accurate. There is an algorithm that can generate such an initial velocity model from measured dispersion curve. As soon as this initial velocity model is created, the program will generate theoretical dispersion curve, assuming it is the actual subsurface velocity model at the surveyed site. Of course, it will not be the same as a measured dispersion curve because it was not based on an accurate velocity model. Then program compares the two dispersion curves and analyzes where the discrepancies exist, and then goes back to initial velocity model and updates a certain part of the model, and then regenerate dispersion curve to make another comparison. It will repeat this process in an iterative manner until it comes up with a velocity model whose theoretical dispersion curve matches the measured dispersion curve within a sufficient accuracy, like within 1% difference. The wind turbine site characterization, as illustrated here, is a common application of 1D MASW survey, which produces a profile of shear wave velocity variation with depths at the center of the turbine site. This kind of 1D profile can also be used for seismic site characterization, commonly known as VS30 measurement. The 2D MASW application will repeat 1D survey at successively different locations along the linear survey line to generate multiple number of 1D profiles. All of them will then be used to construct this kind of 2D shear wave velocity cross-section. And then the 3D profiling can also be conducted by using multiple number of 1D profiles or multiple number of 2D cross-sections. Now, why are we dealing with the shear wave velocity? In other words, why is it so important? That is because when it comes to geotechnical engineering, the stiffness of subsurface material is the most important parameter. And then from elastic theory perspective, the seismic shear wave velocity is considered as the best indicator of material's stiffness. For more details, please watch Why Shear Wave Velocity video. And now, why are we using surface waves, not shear waves, to come up with the shear wave velocity? In fact, there are shear wave velocity methods available, like shear wave refraction, shear wave reflection, shear wave downhole, and shear wave crosshole methods. But all of them are relying on the seismic shear waves, which are usually very weak. And therefore, analysis results are unreliable. On the other hand, the surface waves are very, very strong, always taking more than 2/3 of total seismic energy generated. What that means is the surface waves are very easy to generate and record in the field with a very high signal-to-noise ratio, making the subsequent data analysis very simple and effective. Then how are surface waves related to the shear wave velocity? The surface wave velocities are determined by 3 parameters. The first parameter is the shear wave velocity that contributes more than 95%. And the second factor is density, which contributes about 3%. And the last factor is Poisson's ratio, which contributes about 2%. So from this relationship, one may assume estimation of shear wave velocity by using surface wave will have only about 95% accuracy, but that's not true, because in reality, we know very good approximations for density and Poisson's ratio. So actual accuracy of surface wave method to evaluate shear wave velocity can be as high as 99%. For more details, please watch Why Surface Wave for Shear Wave Velocity video.